Hello, in this video we're going to talk about propositional logic. We're going to cover a valid argument and proof sequences. So this example we have the following newspaper headline was printed during murder trial. I am a liar, says murder defendant. Can the jury reach any conclusion from this statement? So we're gonna argue and see if the jury can make a conclusion or not. So here is one case. If the defendant is indeed a liar, then he makes a false statement and therefore he is not a liar. But if the defendant is not a liar, then he made a true statement, so he could not say I'm a liar. The jury here cannot reach any conclusion from this statement. So we use propositional logic, which is deriving a logical conclusion by combining many propositions and using formal logic, hence determining the truth of the argument. And that's what we just did. But let's see, what is an argument? An argument is a sequence of statements in which the conclusion of the initial statement, called the hypothesis, is said to imply the final statement, which is the conclusion. An argument can be presented symbolically as P1, P2, all the way to Pn. These are all hypotheses here, and this will imply Q. So P1 to Pn represent hypothesis and Q represent the conclusion. So when does Q logically follow from P1, P2, Pn? When is Q true based on the truth of P1, P2, Pn? So informally, whenever the truth of the hypothesis leads to the truth of the conclusion. So every time we take the truth from the hypothesis, we assume this is true, and based on some proof sequence, we reach that Q is also true. We're gonna say that the whole argument is true. Note, we need to focus on the relationship of the conclusion to the hypothesis, and not just any knowledge we might have about the conclusion Q. For example, this example here, we have P1, P2, and Q are all correct statement, true statement. But the relation between P1 and P2 doesn't lead us to Q. So as you see here, P1, Neil Armstrong was the first human to step on the moon. P2, Mars is the red planet. Based on these two hypotheses, can we conclude that no human ever been to Mars? No. This well-formed formula here, P1 and P2 implies Q, is not a tautology, because even though P1 and P2 true, we have to get into Q based on some proof sequence from P1 and P2. So again, this is not a tautology, because even though, so again, this is not a tautology, because even though each of the individually So, definition of valid argument. An argument is valid is whenever the hypotheses are all true, the conclusion must also be true. A valid argument is intrinsically true. P1 and P2 all the way Pn. If this is true and Q is tautology. How to derive the valid argument? Using where we're going to use proof sequence. But here I just want to stop for a moment. Why is, for example, we have A implies B and A, therefore I could conclude that B. We're going to prove this, we're going to using proof sequence, but also using this truth table. So let's fill it up, this truth table. So these are the inputs of A and B. So the only time A implies B is false is when true leads to false, otherwise it's true. Now A implies B and A. So you take the last column and with an and connective, it's the only time it's true when both of them are true. Otherwise it's all false. Now you take this last column and do an implication with B. So again, implication, the only time is false when true leads to false. We have true leads to true, but nothing else. All false leads to anything is true. So what do we say? A implies, if you have 1, A implies B, and 2, assume this is true, and B is also, and A is also true, and A is also true. 3, my conclusion is that B is also true. This is a tautology, so it's always valid. And therefore, we're going to see this. This is modest tolerance. We're going to see it later. We call it MP. We're going to go over it later. So proof sequence. What do we have? A proof sequence is a sequence of well-formed formula in which each well-formed formula is either hypothesis or a result of applying one of the formal system's derivation rules to earlier well-formed in a sequence. So we have two types of forms. We have equivalence and inference rules. So for equivalence, here is some equivalence rules. So these rules state that certain pair of well-formed formulas, like this one here, are equivalent to this one here. And hence, one can be substituted for the other with no change to truth value. So here we go over them. We have commutative law is that when you have A and B and A, or R and S, and within and or, you could flip them and it's still the same. This is similar in addition property. We say 2 plus 3 or 3 plus 2 is the same. And the other one is associative property or associative rule. Just like in addition, 2 plus 3 plus 4 is the same as 2 plus 3 plus 4. So we call this associative as long as it's all and or all or. The next one we deal with is De Morgan's, is very important rule, is that when you have R or S not, you're going to distribute the not and change the and or to an and to an or. And this one we already did the truth table implication, and we call it shortened for IMP, implication. And not R or S is equivalent to stating R implies S. And we've seen an example in previous video where we have either you do your homework or you'll flunk. It's similar to if you do not do your homework, then you'll flunk. So the negation of R was either you do your homework, doing your homework is not R, and therefore negate that will be if you do not do your homework, then you'll flunk. So this is a very important concept. We'll be using it a lot. And so double negation is when you take R and you double the negation, you go back to R. And we've seen equivalent relationship as if then, if P then Q, and if Q then P. So these are the equivalence rules. The inference rule, on the other hand, these rules allow us to add a well-formed formula to the last part of this proof sequence. If one or more well-formed formula that match the first part already exist in the proof sequence. So if we already know that R implies S is true, and we already know R is true, we could infer, we could come to the conclusion or derive S is also true. And this is the example I did earlier, modus ponens, which is the mode that affirms. This is in Latin. The other mode we have, modus tollens, which is the mode that denies, is this way. When you already know that R implies S is true, and you already know not S is true, then you could derive not R. And you call it empty. You have MP and empty. If you already know R is true and S is true, then R and S is also true as an argument statement. So we call it conjunction. And simplification is when you have both of them true. So you could say either R is true and S is true. So you could take separately each one of them. And if you have R is true, R or anything else is true. And if you remind you of the truth table, R is true, R or S true if one of them is true. So if we know R is already true, therefore you could add anything to with the or, and it will be true. We're saying note that the rules do not work in both directions when you're talking about the inference rule. So when you have this, so note that the inference rule do not work in both directions. So from here you could derive this, but you don't go backward, as we're going to see some examples. Use the propositional logic to prove that A implies B implies C is equivalent to A and B implies C. So of course you could use a truth table, but here the question is asking use the propositional logic. So I could see here that I'm going to use some set of equivalent relationship, and I'll go from one side to the other. A implies B implies C. This is equivalent to A implies not B or C. What I used now is implication. Please look back at the table and you see that B implies C is equivalent to not B or C. And this is also, last step is, what can we say? We could do another implication here where I could say not A or not B or C. Also, if I use the associative law, which is moving those parentheses, where not A or not B or C. And why I'm doing all of this, I keep in mind that my goal is to get to A and B implies C. So now I see that I could use De Morgan's law. And De Morgan's, if you look back at the table, look at it. This can be written as A and B, not, or C, of course. This is also equivalent to stating now, back to implication, where The whole thing here is you're not R or S, if you remember. This is similar to or equivalent to R implies S. And instead of R, I have A and B implies C. Now we went from one side to the other with some equivalent relationship, and the reason why we moved from one step to the other. And this is how we do propositional logic for some proofs. Here I just use equivalence, I didn't use inference rules. Here we used the equivalence rules, but not the inference rules. Let's look at some examples of inference rules. So here I put this table here just to remind you of all the equivalence and inference rules. So we have, if Marta is the author, then the book is a fiction, but the book is a non-fiction. Therefore, Marta is not the author. Here they just want us to know which of these